Hello, wonderful people! Here we are, chapter 33, electric fields. This is section 6, electrical energy storage. And that's a title, but everybody knows you store energy in a capacitor. So there's that word, capacitor. This section is, I'll just read it. The electrical energy stored in a capacitor comes from the work done to charge it. That makes good sense. We'll take this sentence apart. First off, let's look at the word capacitor. In fact, I even put this word, there it is. The word capacitor comes from the word capacity. So what does it mean if something has some capacity? It has the ability to do something. It can hold something. And that is exactly what a capacitor does. It has the ability to store electrical energy. It has the capacity to hold, store, charge. Work done to charge it. Stored charge. Okay? Now, this is the sentence that comes right out of the book, and I like that just fine. But then I wanted to break that sentence up a little bit. The electrical energy stored in a capacitor. And why is it stored in a capacitor? Because it has the capacity to store electrical energy. So the electrical energy stored in a capacitor, where does that come from? Where does the electrical energy come from? It comes from the work that was done to charge the capacitor. So to charge the capacitor, that requires work. So you can just imagine that means that you have to stuff a bunch of charges into the capacitor. And if you're stuffing a bunch of electrons into a capacitor, well, we all know electrons repel. So as you stuff those electrons into the capacitor, they're going to resist having any more electrons stuffed in there. So stuffing those electrons in requires work. Does that make sense? How do you like that? I like it. All right. Electrical energy can be stored in a device called a capacitor. Computer memories use very tiny capacitors to store the ones and zeros of the binary code. You do know that computers work on ones and zeros, right? And photo flash units. So when you have a camera and it makes a flash, the flash is done with capacitors. Another place where I see capacitors used all the time are in the giant lasers and national laboratories. Okay, so the simplest capacitor is a pair of conducting plates separated by a small distance, but not touching one another. If this plate was touching that plate with the positives and the negatives that are attracting each other, if the plates touched, well, then the charges would just march across and all pair up and all go to zero. So the key is it's not touching one another. The charge is transferred from one plate to the other, and the capacitor plates then have equal and opposite charge. So if you have the negative going there and the positive going there, these plates are attracting charges, so they pile up because they're attracting each other. The charging process is complete when the potential difference between the plates equals the potential difference between the battery terminals. I don't like that sentence because it uses the word potential difference. And what do we call potential difference? Voltage. So if this battery has, well, it looks like a car battery, so we'll say 12 volts, then that means that the difference between these plates is 12 volts when it's fully charged. The greater the battery voltage and the larger and closer the plates, the greater the charge that is stored. So if you bring those plates even closer together, opposites attract. And if there's more energy pulling those two together, then that's how you have more energy in the capacitor. So you get the plates close together. How close can you get those? Well, you could just put a piece of paper between the plates and then fold them up and then push them together. And Actually, that's exactly how these kinds of capacitors that you see in everyday life are made. In practice, the plates may be thin metallic foils separated by a thin sheet of paper. This paper sandwich is then rolled up to save space and may be inserted into a cylinder. So the two metal rods coming out of there are each one is connected to one of the plates, and the paper is in between them. Not so hard to make. Now, a charge capacitor is discharged when a conducting path is provided between the plates. So if you want a conducting path between the plates, all you have to do is touch that metal and that metal together, and now you have a conducting path. Or you could put something between them, like your finger, and then you'll feel the electricity going between those. Now, if this has a really high voltage or a really high current, it could hurt you, such as discharging a capacitor can be a shocking experience if you happen to be the conducting path. The energy transfer can be fatal where voltages are high, such as the power supply in a TV set, even if that set has been turned off. Now, this is true when I was a kid in the 70s, 80s, and 90s. But nowadays, all the TVs are flat screens. Now, flat screens do have capacitors in them, and some of them are dangerous. But the TVs that were the big, they called them cathode ray tubes, they were a huge chunk of glass. Those had capacitors that could kill you if you just happened to stick your hand in there and touch the wrong thing. And those capacitors would be charged even if the TV had been turned off and unplugged and had been sitting there for like a month. So you could have a TV that was sitting there unplugged, doing nothing for a whole month. And if you took the back off and stuck your hand in there, it wouldn't be hard, wouldn't be easy, but it wouldn't be hard for your hand to hit the capacitor and it would kill you. So back when I was a kid, people made a big deal about this. Don't mess with the TV. I hope people are still making a big deal of that because even these new flat screens have capacitors in them. They don't have the huge ones like they did in the old CRTs. But electricity is always dangerous. So, okay. Moving on. Next bit. The energy stored in the capacitor comes from the work done to charge it. The energy is in the form of the electric field between its plates. And electric fields are storehouses of energy. So you can put energy into the field and have that field just store the energy for you. Where does the energy stored in a capacitor come from? It comes from the work done to charge it. Excuse me. It comes from the work done to charge it. Comes from the work done to charge it. Do you think that might be important in this? So, I could spend a lot of time talking about what a capacitor looks like or how it's built, but the lab does such a better job of that. You just see it, and it just makes sense because you're sitting there looking at it. So I will call this done, and I'll leave the rest to the lab. Thank you very much.